Okay, so gases. So gases, we're going to talk about the kinetic theory. So what we say are these gases, they're particles that are in all forms, and they're constantly in motion. These particles are constantly moving. And for gases, when we talk about this, the kinetic theory is only valid when they're extremely low density. So you have a hot air balloon. Hot air balloon, it's filled with just air, but the air is warm. And because the air in here, okay, is warmer than the air out here, there's a density difference. And that's what causes that balloon to rise. Are there any questions about that? And then as it rises, those particles, those air particles are moving and they're hitting the sides of that balloon. And that's what causes the pressure to keep it inflated. So the kinetic molecular theory, I call this KMT. There are several postulates. One of the postulates says that gas particles are molecules or atoms, and this is what we know about them. We treat them this way. We treat them as their hard spheres. All right? They have negligible volume, so they're not very, the size of them are very, very small. The particles are far apart, okay, especially compared to their size. They might be, instead of being really close together, they're going to be really far apart. Like maybe 2 or 3 times their size apart. And these particles, they're not attracted to each other, but they're not repelled to each other. Okay, so no forces of attraction or repulsion. Now, these particles are always in constant random motion. They are zooming. They don't have any specific place where they're going, and they never stop. If they stop, then they've become solid. So there's our particles zooming along. And what we say is when they collide, the collision is elastic. That means they don't lose any energy. Okay, or they don't gain energy. When it hits another particle or when it hits the side of a container, it's not losing or gaining energy. The energy stays the same. So it's elastic collision. And here you see these particles are sitting there bouncing off each other. They're not gaining or losing any energy as they move. Any questions on KMT? Put the phone away, please. Okay, so kinetic energy. So these molecules have kinetic energy. And kinetic energy is that energy of motion from it being in movement. So what happens is we heat a gas up. It increases, it gets some thermal energy from the heat, and then that is converted to kinetic energy, motion. And so what happens is when we start heating up a gas, the gas particles start moving faster. And this energy that it gets, that it increases, is directly proportional to its Kelvin temperature. Now, in here, we don't talk about Fahrenheit. We do temperature in degrees Celsius. But there's a problem when we talk about degrees Celsius, when we talk about gases, because we can go past 0 degrees Celsius. We can have a negative value. So we want to deal in an absolute temperature. And that absolute temperature is called Kelvin. Not Kevin or Calvin. It is Kelvin. And it is represented with a big K. So you're going to have to do conversions. because we don't have something that just goes out and measures in Kelvin. So if I told you that the temperature in here right now is 25 degrees Celsius, and I want to know what is the Kelvin temperature, Kelvin temperature is equal to our degrees Celsius plus 273. So if it's 0 degrees Celsius, then our Kelvin temperature is 273. If it's 25 degrees Celsius, then our Kelvin temperature is 298. Okay, 298 Kelvin. That's the temperature in here. If we get to 0 Kelvin, that's called absolute zero, which means all particles cease motion. And we've never been able to reach absolute zero. Okay? So any questions over that? Absolute temperature. So when I say it's an absolute temperature, I mean it's in Kelvin. Okay. So here we go. I'm heating up this gas. Heat. What happens to the particles? They start to speed up. Okay? So it's directly proportional. So what I say is if we heat them up, we speed them up. Okay? So heat them up, speed them up. That's what's going on when we have increased the temperature. So what is gas pressure? The definition of pressure is that force that's exerted on our container by those collisions of the gas particles. So those gas particles will hit the side of a container, and that force per that area is called the pressure. Okay? So your soda can is under pressure. What happens when you leave a closed soda in your car and it's 105 degrees outside? It explodes.
Well, yeah, doesn't that happen too?
It happens. It explodes. Why does it explode? What happened? We increased the temperature, which increased the pressure. Yes, I did that 2 summers ago. I left a 12-pack of soda in my trunk of my car.
You wasted.
That was a big mess.
It was a big mess.
What kind of soda was it?
Dr. Pepper.
Ooh.
Diet Dr. Pepper.
Oh, never mind.
All right, so atmospheric pressure, what we're going to talk about, this is the pressure that results on objects because of the air molecules. So this is the pressure that's being upon us or on this wall or whatever pressure, object here and now, what is on us is atmospheric pressure. And that's just those air particles. Now if we go up in elevation, the air gets less dense, and so the pressure goes down. What happens when you go down in the ocean and you go scuba diving? What happens to the pressure? It increases, okay? All right, so how do we measure pressure? We measure it with something called a barometer.
Oh, it's a
A barometer. A barometer. Now, what a barometer does is, this is one that measures, this is mercury. Mercury is liquid. And what happens is we have this reservoir, we have this tube, inverted tube, it has these markings on it, and they're in millimeters. And the air, pressure from the air, pushes down on this mercury, and it causes the mercury to rise up the barometer. And whatever it rises to, right here, that's what the air pressure is. So if it goes up 760 millimeters, we say that the pressure is 760 millimeters of mercury. Okay. So there are several units of pressure. The SI unit is just Pascal. Standard pressure, what we feel on us, is 101 kilopascals. A millimeter of mercury is how high it is to support or to go up 1 millimeter of high. And then we have something called STP. STP, please highlight it, mark it, know it. When I say something is at STP, I am telling you two things. I am telling you that it is at 1 atmosphere and 0 degrees Celsius. STP stands for standard temperature and pressure. And that is 0 degrees Celsius and 1 atmosphere. So if we need an absolute value, what's the standard temperature and absolute value? What's it in K, in Kelvin? 273, okay? You have to know these conversions. I like to do things in atmospheres, but sometimes you're not going to get it in atmospheres. So 1 atmosphere is equal to 760 millimeters of mercury, which is equal to 760 torr, which is another unit, which is equal to 101.3 kilopascals. So you need to be able to convert. If I say something is in 780 millimeters of mercury, what's the atmospheric pressure? So what do we need to do? We know that for every 1 atmosphere, there are 760 millimeters of mercury. And you do that math and you get like 100.02 or something. 02 atmospheres. Okay? So you got to pay attention to that information. All right. And those conversions will be on the board on the day of the test. Quizzes, whatever. And yes, he is back. Avogadro. Avogadro says equal volumes of gases at the same temperature have equal number of particles. And what he says is, so if we're at standard temperature and pressure, then the volume of all these gases are the same. So at standard temperature and pressure, at STP, all gases have a volume of 22.4 liters. That's going to become really important to us later in the week. All gases at STP have a volume of 22.4 liters.
Is that something where you need to know for like the conversions and stuff?
Yes. So I can ask you several, we're going to learn an equation and you either have to do some stoichiometry or you might have to use some equations. You might do both. Any questions over that? All right. So properties of gases. These are compressible, and there's certain variables that we're going to look at gases. One is their volume. We're going to look at the pressure that they may exert. We're going to look at the Kelvin temperature. So what temperature are they at? And we're going to look at the number of moles. So these are the variables that you're going to see that in the parentheses. That's what it's going to look like in an equation. And then we have units. Yes? It's an N. Moles is an N. That's just the way it is. So pressure can be in several units. It can be in atmospheres. It can be in millimeters of mercury. It could be in torr. Or it can be in kilopascals. So those are the different units that we're going to see pressure in. Volume, what's the base unit for volume? Liters. So volume is going to be in liters. Kelvin temperature, the unit is K. And moles, the unit is mole. So those in red, those are your units that you're going to see. KPA, yes, kilopascal. So your soccer ball is under air pressure. Your airbags, when you have an accident and your airbag gets released, you have two gases or two compounds that are separated. And what happens when you have an accident is one of those, the bag that separates them or whatever's separating them gets busted, and they start the reaction, and boom, it fills up with gas to help save your life. Okay? So let's think about this. What do you think is going to happen if we add or remove a gas? How is that going to affect gas pressure? So if we add a gas, what happens to the number of particles? We're going to increase the number of particles. Now, when I increase those number of particles, what's going to happen is they're going to start colliding more. Okay, so here we are in this classroom. Everybody's out except for I have Cameron and Oscar in here, and they're running around like fools. Just running around. They're not attracted nor repulsed by each other, so they're just going. So their likelihood of colliding is going to be small. Okay? Now, I bring all of you guys in here, and you guys are all running around like fools. And then, so what's going to happen with those collisions? It's going to increase. We're going to start hitting each other. Okay? And when that happens, what's going to happen to Mrs. White's blood pressure? It's going to go up. Okay? But now what if I take out some gas? I take some of you guys out. What's going to happen to the number of particles? The particle's going to go down. Which means we're not going to be colliding as much. So our collisions are going to go down. And Mrs. White's blood pressure is now going to go down because it's nice and calm again. Okay? I know. So you can put decrease, increase. I do arrows, up arrows, down arrows, whatever you want to do. Any questions on that? Okay. Now, if I have more particles in here, what's going to happen to the pressure? It's going to increase, okay? So adding particles is going to make the pressure increase, which means what type of relationship is it? It's direct. One goes up, the other one goes up. Okay? So a lot of this is just looking at those concepts. It's saying what's going on. Okay. What if we change the size of the container? What if we're all in here running around and I take you guys and I put you into a smaller room? What if I decrease the size? We're going to be bumping what's going to happen to the number of collisions? It's going to, if we decrease the volume, then we're going to increase the number of collisions, which means we're going to do what with the pressure? We're going to increase the pressure. If we increase the volume, we go out into the commons and we're out running around, we're going to have way less collisions, and the pressure is going to go down. Okay? So this is an inverse relationship. When one goes up, the other one goes down. Yes?
But you said they run into each other, they don't lose energy or
No. They just bounce off each other. That's what the elastic means.
Unlike us.
Okay. Okay. So volume and pressure indirectly related. Please draw this graph so you know what it looks like. If I have my volume and I have my pressure, if I start decreasing my volume, my pressure starts going up. Okay? So this is an indirect relationship. So if I increase pressure, then the volume is going to go down. Okay? So if I compress this gas, when I start compressing that gas, my temperature is going to go up. when I expand the gas, then it's going to go down. The temperature starts to go down. Okay, so you need to know that these are pressure and volume are indirectly related. So when I increase volume, I decrease pressure, and vice versa. And I do this, arrows, everything. When I'm working math problems, I predict what's going to happen, what should be happening. If I increase the pressure, what should happen to my volume? The volume probably should go down.
I know what you said.
If I increase my pressure, what would happen to my volume? Decrease. All right, what if I heat or cool a gas? Now, if I heat or cool a gas, heat them up, speed them up. That means my energy goes up, which means we're going to increase collisions because we're all going faster, which means we're going to increase the pressure. Okay, so you need to know this graph, be able to look and say V versus T, it's a direct relationship. Increasing my temperature increases the volume.
But I thought if you increase volume, then the pressure.
Okay, we're keeping pressure constant. If we're keeping pressure constant.
Okay, so
See, pressure is not changing here.
increase. So then does it actually?
Increases temperature, increase volume. Now, if we cool, what happens to a gas when you cool? What happens to steam when you cool it? Steam becomes what? Liquid water, which becomes what? As we still, becomes ice, becomes a solid. Okay? So when we decrease the temperature, we decrease the energy, which means that they're not moving around as much, which means we have less collisions, which means the pressure is going to go down. Eventually, if we cool it down far enough, it becomes solid.
It's almost like if you let it around, you're going to get hotter.
Wait a minute, but gas can't get solid.
Yes, yes. Dry ice?
But gasoline can get solid?
No, we're just talking about gas,
Oh,
gas.
yeah.
Okay. So factors that affect a pressure, heating or cooling. So we need to be in Kelvin. We have to be in Kelvin because what happens if I multiply by 0? What do I get? 0. What happens if I divide by 0? You can't. You get arrow, right? So that's why we use absolute temperature. That's why we use Kelvin. Okay, I'm going to skip this. So we're going to look at the 4 gases, gas laws. And we are assuming,
Wait, is this your continuing lecture? No. We're done.
I'm going to go through Charles' law. Oh, yeah. No, Boyle's law says the following. So we have Robert Boyle. He did some studies, and he said that if I have this mass of this gas, and I increase the pressure, then the volume went down, and vice versa. So he's the one that says that we have this inverse relationship. So if I increase pressure, I decrease volume, and vice versa. So the equation that we use, keeping temperature constant, is P1V1 is equal to P2V2. So we boil, peas and vegetables. Okay, so boil is P and V. All right, so if I have a gas and it's at 1 atmosphere and the volume of it is 5 liters, if I change the pressure to 0.5 atmospheres, we want to know the new volume. So, first of all, make a prediction. What happened? What did I do to my pressure? I decreased my pressure, which means my volume better do what? It better go up. So if we look at this and we solve for x, 5 divided by 0.5 is 10. 10 liters. So it went up. I like to look at those little concepts and saying, I know this relationship, this is what it needs to do. And if my answer doesn't do that, then I know I messed up somewhere.
So we're going to have to know, like, atmosphere
All right. So a gas is collected in 242 milliliter container. So what variable is that? Volume. It's the first volume I ran into, so I'm going to call it volume 1. The pressure of the gas in that container is 87.6 kPa. So that volume is 87.6, or pressure 87.6 kPa. What is the volume if we change the pressure to 101.3 kPa? First of all, what did we do to the pressure? We took the pressure and we increased it. So my answer says what? My volume better do what? Go up or down? My volume better go down. So let's set this equation up. So peas and vegetables. So my first pressure is 87.6. My volume is 252. 42? Oops. Uh-oh. I wrote it wrong up there. Sorry. That's 42.
That's all good.
So 242. My new pressure is 101.3. And my volume is what we're looking for. So solve for X. Yes?
Alright, since it's in milliliters, do we have to change it?
Okay, so he asked, since this is in milliliters, do we need to change it to liters? If it said, what's your volume in liters? This is one where we can leave it in milliliters. Okay. You can change it, that's fine. So our answer should be 209 milliliters. Did our volume go down? Yes. So, we're right. So, your homework tonight is there's 5 of these problems. I'm going to go to Charles's Law and go over Charles's Law because you'll have a worksheet over Charles tomorrow. Okay. So, moving on to Charles. Oh. This, if you are in PowerPoint, it's going, or in homeroom, it walks you through those equations. I don't rearrange before. I like to solve.
Only if you download it into like if you download it into like GoodNotes, it won't.
It doesn't fly through. It's just. We're gonna skip that. All right. So Charles. Now, what Charles's law says is that we're looking at temperature and volume. So this, what he saw was that if we had kept our pressure constant and we increased the temperature, then what happened was the volume would increase. So he said that this was a direct relationship. If I increase T, then what happens? The volume goes up. So increase T, increase volume. So you see this graph, you see what it looks like, and the equation is V over T is equal to V over T. So Charlie, for Charles's law, Charlie Brown's Christmas was on TV. So V over T. Again, all these equations will be on the board. Okay, so let's do an example. A sample of gas at 15 degrees Celsius. So that is what? That is temperature. And it's at 15 degrees Celsius. But we know that we have to convert that to K. So we add 273. 288. And 1 atmosphere. So I'm going to put pressure is 1 atm. And the volume is 2.58 liters.
Yeah, that's why I was confused. Like, why do you need another picture?
I just write everything down.
Oh, okay.
What volume of this gas will occupy at 38 degrees Celsius plus 273. What is that? 311. And the pressure is at 1 atm. So when I look at this and I see I've got T, P's, and V's, this is held constant, right? So the P means nothing. Now we put V over T. So make a prediction. What did we do with our temperature? We increased our temperature, so what should happen to our volume? It should go up. So,
Okay, I was thinking about, okay, never mind.
so 2.58 over 288 is equal to X over 311. So how do we solve this? We do the butterfly method, cross multiply. Somebody tip me the X. Somebody cross multiply that for me.
270. Wait, what's supposed to go? Is it supposed to go up?
Multiply 311.
It should go up. Yeah.
278.
278.
Well, 279 if you're rounding.
So 2.
Wait a minute.
Well,
Do 311 times 2.58 and divided by 2. It's 2.78.
2.78.
Or 2.78.
Yeah, I said, but then you can round it to. Okay.
Oh, I didn't hear the point.
Yeah.
2.78. Our unit is what? Is liters. Did it go up? Yes. So we did it right.
And that's it.
No, but I am going to. Oh, I hope. I don't have my popsicle sticks today. I'll bring popsicle sticks, and what we'll do is we'll have a popsicle stick, and we'll label. We'll put our V and our P and T's. And what happens is if you like decrease the V, you see that the P goes up or whatever. So I'll bring popsicle sticks so that you can have it in hand. Are there any questions? So tomorrow, and then on tomorrow's assignment, so your assignment tonight is Boyle's Law. You won't have any homework tomorrow if you don't, because you're just going to turn it in. But Charles's Law will be your, you'll have to work some of those. And then on the back side, if you get to that, it'll be another law, but it's worked just the same. We'll just change the variables. So are there any questions?
Can you go back to the slide with the graph of the volume and temperature?
Okay, hold on. Let me stop this real quick.